Okay, hello guys. This is section 6.4, video 1, logarithmic function. So it's a brand new topic. I just want to let you know, just be patient with logarithmic functions. For most of you, it will be new topic. For some of you, you heard about logarithmic functions, but in high school, I know we didn't spend a lot of time on logarithmic functions, so it's just learning like a new language. Okay, we have to get used to them. So let me give you the definition. Logarithmic function is the inverse of the exponential function. Okay, so we have y equal log of base a of x. Okay, so logarithmic function also has a base. This is how you read it. Read as y is the logarithm with base a of x. Okay, so x is input, y is our output. So the definition of logarithmic function is the inverse of exponential function. Y it's equal log base with base a of x if and only if, since logarithmic function's inverse of exponential function, base a to the power of y is equal to x. Okay, so let me just rewrite that. Y is equal log base a of x if and only if a, which is the base to the power of y, will give you x. Since log and exponential are inverses, so like you guys see, those two expressions are equivalent. And for inverses, you guys know already that x and y switching. So we're going to learn how to change logarithmic function to exponential. Base all the time is going to be base, but like you see, if you're switching from log to exponential, next to base, you're going to have y, and outside you're going to have an x, okay, because they are inverses. And in inverses, x and y switch, okay? So let's just quickly catch up that index a is base. Okay, base, what we know about base, like with exponents, base has to be a real number greater than 1. Greater than 0. And a can't be 1. So that's the information about base. Okay. Domain, I will talk about the domain when we'll be graphing, okay? Or maybe just right here, okay? And x, right here, going back to log, but the explanation will come with the graph. The domain has to be greater than 0, okay? So one note which may help you. So when you need to evaluate logarithmic function, log of base a, that base it's like below, it's an index of x. It will help you if you will think base raised to what power gives me x? Gives me x, okay, which is the number next to log. Okay, so think that way. Base raised to what power, okay, will give you x. Okay, let's do the examples. Okay, so here what we're going to focus, we're going to change, going to see examples when we're going to change exponential statement to logarithmic statement. Okay, and I'm going to use the example from your textbook. This is page 448, number 11. Okay, we have 9 equal 3 to a second power. So this is exponential. And we need to change to log. Change to logarithmic. So just remember that logarithmic statements and exponential statements are inverses. So what's going to help you? Always identify what is the base, because base of exponential function, it's always the same as base of logarithmic function. So note, base of exponential function is always the same as the base of the logarithmic function. Okay, so what I know that I have to create a function which is logarithmic. Y is equal log base a of x. We need to create something like this. So first what you want to do, you want to identify the base of exponential function. So the base, it's right here. Okay, the base of exponents, it's the number in front of the exponent. Okay, so we know that the base it's equal to 3. So our function will be y equal log base 3 of x. And now we need to figure out what will be x, what will be y. So since exponential function and logarithmic function, they are inverses of each other, so you're going to switch, okay? So look what happened here. So when you have that base 3 of log, so before, okay, next to base you had 2. So when you switching to log, 2 and 9 we switch the position, okay? So you're going to have next to base, right now you're going to have 9, and outside you're going to have 2, okay? And that's definitely makes sense because the definition of log is base. So again, switch, you're always switching x with y, okay? So the definition of log is base raised to which power will give you x, okay? So in our case, it's 3 raised to which power, which is will give us 9. So definitely It's 3 to a second power, which is equal 9, and that's what we had it. Okay, so figure out what is the base when you're switching, and then switch the numbers from exponential, okay? Because x and y is going to switch. Let's do number 16. This is number 16, also from page 448. So in number 16, okay, they give you 3 to the power of x, it's equal 4.6. So you have exponential function, and do the same thing, figure out what is the base. So the base it's 3. Base it's equal 3. So now I have to switch and create equivalent logarithmic function, which is the inverse of exponential. So what I know? Okay, I know that my logarithmic function has to have a base. What base we're going to have? Exactly the same like the base of the exponent, so we're going to have 3. Now, what's going to be next to base? Okay, exponential function has 3. Since logarithmic function is inverse of exponential function, so those two will switch the position when you're switching to logarithmic function. So I'm going to have log of base 3 of 4.6, it's equal 3. Okay, so from exponential, we switch to logarithmic function. So figure out what is the base always, and then switch the remaining two numbers. Okay, oops. Okay, next, example 2. Next example. Here we're going to, in this example, we're going to change logarithmic statements to exponential statements. Okay, and I'm going to use a couple problems from your textbook. So all of them are on page 448. And the first one, which I'm going to solve, it's number 19. So here we're doing the opposite. They give you the logarithmic function first. You have logarithmic function of base 2 of 8, it's equal 3. So you have logarithmic function of base, and the base, it's always that index right here of base 2. So now you need to create the inverse, technically, which is the exponential function. So don't forget, with inverse x and y switch. So now we need exponential function. So we need base, you need exponent equal to something. So that's what we're going to create. So base of log and base of exponents, they always equal. So in our case, we're going to have base of equal 2. Now we need exponent equal to something. So we have a base. Since log and logarithmic function are inverses, so you're going to switch 3 with 8. So they're going to switch the position. So right now, next to base, it's going to be 3. And 8 will be outside. And always check if that makes sense. 2 to the third power should be equal 8. That's definitely it's true. So this is our answer. Okay, let's do a little more. So that was number 19. Let's do number 20. In number 20, they give you log base 3. And like you see that base 3, it's like a little below of log of 1 over 9 equal -2. So you need to create the exponential. So base of this log is equal 3. So when you create exponential function, so your exponential function will have the same base, which will be 3. And now we just need exponent, equal, and number. So we have a base. When you figure out what is the base, the rest should become quick since they are inverses 1, 9 over 9 and -2 switch position. So right now, an exponential function next to base, it's going to be -2. And outside, you're going to have 1 over 9. And that definitely makes sense because 3 to the power of -2, okay, you don't need to really prove it, but just explanation. 3 to the power of -2, when you have negative exponents, that means you take the reciprocal of the base, so you're getting 1 over 3, and then exponents become positive. So you're getting 1 to a second power and 3 to a second power, which is 1 over 9. And that's what we end up with. So always when you're changing, especially at the beginning, make sure that's what you're doing, that the exponential equation which you create makes sense and it's correct. Okay, let's do 26. I want to talk about 26 because it's a little different from the same page. In 26, you have natural log x equal 4. So I want to explain it that ln read as a natural log is the logarithmic function with base equal to e, okay? And we know e from exponential functions, irrational number, it's about 2.71. Okay, so when you see ln of x, technically, this is the same as log of base e, okay, which is about 2.71. Since log and e, log already has letters, and then you put in base e as a letter. So just to trying to avoid, I guess, confusion, all the time when your logarithmic function has base e, we're using that shortcut, and we're just putting as a ln of x, which we call natural log. Logarithmic function. So in this example, you have ln of x equal 4. So what you guys need to remember, you need to remember that the base of this log is e. Okay, so you need to create exponential. Okay, so we need the exponential function. Our exponential function has to have a base. Base of our exponential function is going to be the same as the base of log. So it's going to be e, okay? And now, when you figure out what is the base, the other expression or numbers will change the position. So your exponential function next to base, it's not going to be x anymore. It's going to be 4. So e to the power of 4, it has to be equal to x. Okay. Okay, so this is the answer. And one more example like this. And I think we good with those type of examples. This is number 24, again from the same page, which is 448. Change this logarithmic function, log base 2 of 6 equal x to exponential. So always start with figure out what is the base. Base of log is equal to the base of exponent, so we're having 2. And since the exponential function, logarithmic function are inverses, so the remaining expressions or numbers will switch the position. So now next to base, it's going to be x, and 6 will be outside. Okay, and this is the answer. Okay, so I teach you how to change logarithmic function to exponential function and how to change from exponential function to logarithmic function. Why we can make that change? Because again, they are inverses. Excuse me. Very important that you know how to do it because we will use that later with solving equations. Now, I'm going to talk about examples of how to find the exact value of logarithmic functions. So next you're going to see examples of finding the exact value of a logarithmic expression. And here I'm going to use also a couple problems from your textbook. I don't want to use the examples from, explain examples from your textbook because you can always study them by yourself. So I'm trying to give you different ones. So this is number 27 from page 449. Okay, so you need to find the exact value of logarithm of base 2 of 1 equal to what? Okay, so you have to think that way. Okay, log base 2 of 1. Okay, so definition of log. Okay, let's go back to that definition of logarithmic function. So you have y is equal log of base a of x means, and you create that exponential, the inverse, that base to the power of y has to give you that x. So here you have to think base, which is 2, to which power will give you 1, because 1 is x, the expression next to log. Okay, so that only work when 2 is going to be bring to the power of 0. That will give me 1. Okay, so our answer will be 0. And maybe let's just replace that question mark with y, so that would be better. 2 to what power will give you 1? So y has to be 0. So that means y is equal 0. Okay, so answer, logarithm of base 2 of 1 is equal 0. Because 2, again, if you change that to exponential, because 2 to the power of 0, it's equal 1. Okay, so that was the answer, 0. Let's do more. 27, let's do 32. So this is without using calculator. 32. You have to evaluate what is log of base 1 over 3 of 9 equal to. So again, I will put that y. So if you change that to exponential, so you will have, again, let me just write this down. So change to exponential. Statement, and that will help you to evaluate that. So the base of log is 1/3. So our exponential will be base 1/3 to the power of y will have to be equal 9. And this is like checking, okay, when 1/3 to what power will give you 9? Okay. Let's try to figure out. Okay. So couple things here. 1/3, hope you guys can relate it, that 1/3 is the same as 3 to the power of -1. So I'm going to rewrite that. 3 to the power of -1. And of course, I have that y. It's equal to 9. And I'm going to rewrite that 9 is the same as 3 to a second power. Okay. So, using the properties of exponents, when you have power of power, you can just multiply them. So you have 3 to the power of -1 times y, which is -y. It has to be the same as 3 to a second power. So now, because technically what you're trying to do, you're trying to figure out what is that y. Okay, so now, since we have the same basis, on the left and on the right side, you can always use 1-to-1 property. Since those two expressions are equal, so what you can do, you can ignore those bases. That means those exponents needs to be equal. So -y has to be equal to 2. Divide each by -1, and y it's equal -2. So this is our answer. Okay, going back to the problem. Logarithm function of base 1/3 of 9, it's equal to what? It's going to be equal to -2. Okay, because 1/3 to the power of -2, it's definitely equal 9. So again, because 1/3, I'm changing that logarithmic function to exponential to the power of -2 has to be equal 9, and that's definitely true. 1/3, excuse me, you see negative exponent, so you take reciprocal, and that exponent become positive. And like you see, this is true. Okay, so the answer is -2. Okay, so I know it takes a little practice, but we just need to learn those little tricks, how to change from log to exponent and from exponents to log. So that was number 32. I want to do more examples like that. Again, I aware of the situation that that can be brand new for you. So 33, from the same page, you have log of base 10 of square root of 10. It's equal to what? So you have to figure out. Okay, so I'm going to put y. Okay, we have to figure out what is log base 10 of square root of 10 equal to. So I'm going to change to exponential because it's easier to solve it that way. Change to exponential. So the base of my exponents, it's going to be the same as base of log. So I'm having 10. And next to my base, I'm not going to have square root of 10 because they're going to switch the position. So I'm going to have 10 to the power of y has to be equal to square root of 10. Okay, so what I recommended to having the same basis on both sides, so you can use that one-to-one property. So we know that square root of 10 is the same as 10 to the power of 1/2. So let me rewrite that as 10 to the power of 1/2. And on the left side, I have 10 to the power of y. And here, use one-to-one property. Since we have the same basis on the left and on the right side, and the expressions are equal, that means exponents needs to be equal. So y it's equal 1/2, which means that's our answer. So log base 10 of square root of 10 is equal 1/2. And that's definitely true, since I'm going to change that to exponential. Since 10 to the power of 1/2, it's equal square root of 10. Okay? So I see log, I change into exponents. If I would see exponents, I would change to log. Okay, 34. Let's do a little more until you guys, okay, I'm tired of that. I do understand what's going on. 34. You have log base 5 of cube root of 25. It's equal to what? So you have to figure out. So let's just rewrite that as log base 5 of cube root of 25. It's equal y. So to figure out what is that y, equal, change to exponential. So the base of my exponents, it's the same as base of log. So we're having 5. And then we need exponents and we need number on the right side. So next to base, it's not going to be cube root of 25 because they are inverses functions. So those expressions will switch the position. So I have 5 to the power of y. It's equal cube root of 25. Okay. So let's rewrite the cube root of 25 as this is the same as 25 to the power of 1/3. Okay. So they are equivalent. Note, when you guys have expression with the radical, let's call this is index n, this is x, and this one has power m. So you can rewrite that. You know what? I will change that. Don't do that yet. Okay. So you can use that the radical can be write as an exponent which has a fraction. So this is the same as x to the power m, the power next to x. It's your numerator, m over n. So using this, very useful, guys, especially with exponents, rewrite cube root of 25 as cube root 25 is the same as 5 to a second power. And you can apply what I just gave you, that formula. So you can rewrite that 5 to the exponent 2 over 3. So they are equivalent. It's the same thing. So going back here, we have 5 to the power of y. It's equal to 5 to the power of 2 over 3. And again, why I want to have a 5? Why I want to have on the right side exponential expression of base 5? Because we can use that one-to-one property. You can just ignore the bases. And since those two expressions are equal, that means exponents has to be equal. So we have y is equal to 2 over 3. And that's our answer. Okay, so going back here, log base 5 of cube root of 25 is equal to 2 over 3. Okay. Next, what we're going to do is we're going to talk about graphs. Okay, so next part of the lecture, it's going to be, I'm going to show you how the graphs of logarithmic function looks like. Since logarithmic functions are inverses of exponential functions, hope you guys remember that when we graph exponential functions, we have two cases. One graph was increasing when the base was greater than 1, and one graph was decreasing when the base of exponents was from 0 to 1. And that's going to happen also to logarithmic functions. So next, okay, we're going to talk about the graphs of y equal log base a of x. Okay. So before we graph it, let me just write a note that let's say f of x, original function, and f to the power of -1 of x is the inverse. So it's very important that we remember that domain of original function is equal to range of inverse function. And range of original function is equal to domain of inverse function. So why am I reviewing this one? Think about that f of x is our exponential function. Okay, exponential function. So I already explained you that the inverse of exponential function is logarithmic function. Okay, so logarithmic function's inverse of exponential function. So what that means? That means that domain of exponential function will be the same as range of inverse, which is of logarithmic function. So domain of exponential function was from -infinity to infinity, which means range of logarithmic function will be from -infinity to infinity. Okay, so that's one. Next, range of exponential has to be the same as domain of logarithmic function. Since we already learned about the exponential function, the range of exponential function was from 0 to infinity. That means domain of logarithmic function will be from 0 to infinity. Okay, and you're going to see that on the graph in a second. Okay, let me just pause for a second. Okay, so let's compare. Okay, okay, let's graph. Okay, so first what I'm going to do, I'm going to review both so you guys can see. So that would be the first case. We're going to talk about increasing graphs. So I'm going to graph first and review how to graph y is equal a to the power of x. Okay, and that will be the case when a is greater than 1. That's why we're talking about increasing graphs. Example, we'll be graphing y is equal to the power of x. So you guys have to remember that to graph exponential function, I teach you to graph it using 3 major points, which was 0, 1, 1, a, negative 1, 1 over a. Okay, so we're graphing exponential functions with 3 points. So in our case, a is equal to, so 1, a will become 1, 2, and negative 1, 1 over 8 will become negative 1 and 1 over 2. So we graphed that last time. Just remember that's those 3 major points to graph it. Okay, it's very useful to memorize them. Y, x. So we have point 0, 1. Okay, y-intercept 1 and 2 right here. So 1, 2, 0, 1, and negative 1, 1/2. Negative 1, 1/2, somewhere here. Ay, what I'm talking about. Sorry. And negative 1, 1/2 right here. Okay, so exponential function. Hope you guys remember that exponential function has horizontal asymptote y equals 0. So y equals 0 is the horizontal asymptote. So that was exponential function. And like you guys see, let's just review. Domain of exponential function was from negative infinity to infinity. You can pick any x you wanted. And the range of exponential function is from 0 to infinity because our graph is only above y equals 0 axis. Now what we're going to do, we're going to create the inverse of that graph. Okay, so this is exponential. Next, what we're doing, we graph y is equal log base a of x, okay, which is the inverse. Okay, and we're going to talk about increasing case. And increasing graph is when base it's greater than 1. So I'm going to use here the inverse of the function which we graph, and we will graph it y is equal log base 2 of x. Okay, because again, I'm creating the inverse of y is equal to the power of x. So they are inverses. So look what happened. To graph logarithmic functions, use three major points. What point are you going to use? You're going to use the inverse of three major points of exponential functions, which you will graph with point 1, comma 0. Like you see I switching the coordinates. You're graphing logarithmic function with a comma 1, and you're graphing logarithmic functions with 1 over a comma negative 1. Okay, so you're always graphing logarithmic functions with those three major points. Okay, in our case, we're going to have 1 comma 0. Again, a in our case it's equal to, so the second point which I will graph will be 2 comma 1, and the third point will be 1 over a, which is 1/2 comma negative 1. So I switch x with y. So let me graph it. Logarithmic function. Okay, 1 comma 0. So we have 1 comma 0, 2 comma 1 here. Okay, I will just switch of writing. I'm not going to put the coordinates, but you guys see it. This is 2 comma 1 right here, and 1/2 negative 1 somewhere here. Okay, so this is the logarithmic function. Slowly increase. So this is y equal log base 2 of x. Okay, so like you see, exponential function, which is in green, and logarithmic function, which is in pink, they should be inverses of each other, which means they are symmetric with respect to the line y equal x. Okay, so couple things. Okay, let's talk about domain. So domain of logarithmic function, like right now you guys see the graph happening on the quadrant 1 and quadrant 4, so we only have x's greater than 0, which you can put in the interval notation from 0 to infinity. That's the domain. Okay, range, we're talking about the y values, right? So range, that's our y values. There's no restriction. We can use any y value, so that means the range will be from negative infinity to positive infinity. So like you see, what used to be the range of right here of exponential function become domain of logarithmic function, and what used to be the domain of exponential function become range of logarithmic function. Okay. Also, what is important, our function is still increase. So function is increasing. Let's compare. Here, exponential function had y-intercept 0, comma 1. Our logarithmic function has x-intercepts 1, comma 0. No y-intercept. Now, our exponential function had y equals 0 as a horizontal asymptote. Our logarithmic function has a vertical asymptote, x equals 0. I don't think it's h over there, asymptote. Okay, and I'm going to stop here. The next video will talk more about graphs and their transformation, and I will graph the case of logarithmic function, the decreasing case. Okay, thank you. Stop recording.